Okay, in this video we're going to take a look at some ways to deal with integrals involving trig functions. Specifically, we're going to look at functions of the form sine to a power times cosine to a power, or secant to a power times tangent to a power. So this will just add to our list of antiderivatives that we were able to find by hand. So we want to evaluate integrals of the form sine to a power times cosine to a power, and then secant to a power times tangent to a power. And our plan of attack is going to be to use U substitution and the power rule for the most part. Now, in the practice set, there's going to be a few sprinkled in there that don't require what we're going to look at in this video. The idea being that you see the difference between when you need to use integration by parts or when you can just do a basic U substitution, as opposed to when you need to do what we're going to take a look at in this set of notes. So let's take a look at this first one. We need to find the antiderivative of sine cubed times cosine to the fourth. Both of them have an argument of x, and we're going to find the antiderivative with respect to x, as indicated by the differential dx. So, as always, we'll start with the integral itself. So sine cubed of x times cosine to the fourth of x dx. And in this case, we're going to want to take sine cubed and write it as a sine squared and a sine. So we'll keep two of them together and then separate out one of them. And then sine squared, as we know from trig, is 1 minus cosine squared. And now we can distribute across that binomial and separate our integrals. So we would end up with, if we distribute, we'd have cosine to the fourth x times sine x, and then negative cosine squared times all of that. We'd have cosine to the sixth sine x dx. So all I did was distribute and then separate the integrals, the antiderivatives. And now for this first one, we can do a U substitution where U is cosine and its derivative, the differential of U, would be sine of x dx. And then for the second integral, we can do the same thing. Let U be cosine, and then du be negative sine also. So using our U substitution, the first one would turn into U to the fourth du, and the second one would turn into U to the sixth du. So we end up with negative 1/5 U to the fifth plus 1/7 U to the seventh plus a constant. So at the very beginning, we couldn't do just a basic U substitution, because if you let U equal sine, then the derivative would be cosine, but we have cosine to the fourth. So we had some extra cosines that we didn't need. If we let U be cosine, then du would be negative sine, but we have sine cubed. So if you try to do a basic U substitution at the beginning, you're not going to find a U that works, that allows us to make a substitution, resulting in one of our known antiderivatives. However, by swapping out a sine squared and distributing, it did result in some integrands that allowed us to U substitute using a basic U substitution. So our plan here So notice we forced sine to have an even power switched it to cosines and saved a sign for du. That was kind of our plan, is we, instead of sine cubed, we made a sine squared, so we could swap that out for some cosines, distribute, and then we left over, we had this sine of x that we didn't use. That way it would be there for the du part later on. So that was kind of our plan for that one. So this next example shows that you don't have to have sine and cosine both raised to some integer power, and the same idea can still work, or same method can still help us out here. So if we have pi to the 6 up to, or pi 6 up to pi thirds, and then we have cosine cubed x over principal square root of sine x with respect to x. Well, let's move the sign up to the numerator. So that would be cosine cubed x sine to the negative 1/2 x dx. And instead of cosine cubed, let's break that up. And let's do cosine squared. And leave a cosine out. Suppose we can put the dx last. And then swap cosine squared out for 1 minus sine squared. And then again, we can just distribute and split up the integrals. So if we distribute, we'll have sine to the negative 1/2 x cosine x dx minus, and then we'd have sine to the 3/2 x cosine x dx. And then again, now we have just a cosine to the first, and that's going to allow us to do a u substitution where u is just sine, so that du will be cosine. We can do the same thing for the other integral. So now we can just do a basic u substitution. Alright, so we make that u substitution, so we'll have u to the negative 1/2, and then we'll have u to the 3/2, and then du will be the cosine. And let's see, we'll end up with, by the time you add 1, we're going to have 2 sine to the 1/2 x minus, by the time you add 1, you're going to get 2/5 sine to the 5/2. And then that's in terms of x, so we're going to go from pi over 6 to pi over 3 using our fundamental theorem. So then we do top minus bottom, so we're going to have 2. So we plug in pi over 3 for sine, so that'll be root 3 over 2 to the 1/2 minus 2/5 root 3 over 2 to the 5/2 minus 2, plug in pi over 6, sine of pi over 6 is 1/2, and we'll just get an approximation for that. So that ends up being approximately 0.239. So that Riemann sum, that definite integral or Riemann sum is approximately 0.239. Trying to write an exact value for that would be kind of a pain, so an approximation would, trying to simplify that, which we could, but I don't know if that's worth our time. So notice for this one, cosine had the odd power, so we forced it to have an even power and saved a cosine. We saved that cosine for the u substitution. So we forced a cosine to the first out of it so that we had that for our du. So it's very similar to the one we did before. And we had a rational exponent this time to deal with, and that didn't really change anything. So in this next example, you can have both exponents be an even integer, and everything, we can still make it work. So if we had cosine to the fourth of x dx, that would be the same thing as cosine to the fourth x times sine to the 0. So they're both even integer exponents. And we don't really need the sine to the 0, but it shows you that it is in the form that we are interested in, cosine to a power, sine to a power. Cosine to the fourth is cosine squared squared. And in trigonometry, we learned that if you have a trig function squared, you can reduce its power with the following identity. So cosine squared is the same thing as 1 plus cosine of double the angle, all divided by 2. So that substitution is going to allow us to reduce this power of 2. So we would have 1 plus cosine, double that angle, over 2 squared. So now it replaces a cosine squared with a cosine to the first. Well, let's go ahead and square that. So if you square that binomial, you end up with 1/4 plus 1/2 cosine 2 times the angle plus 1/4 cosine squared of 2 times the angle dx. Well, we have a cosine squared again, so we're going to use that formula one more time. And let's see what we get. So using that formula one more time, we'd have 1/4 plus 1/2 cosine 2x plus 1/4. Use that formula one more time. 1 plus cosine double the angle. So the angle was 2x, so we doubled it, it's 4x. dx. Now let's collect like terms. We've got 3/8 plus 1/2 cosine 2x plus 1/8 cosine 4x dx. So that's just after collecting like terms, multiplying the 1/4 in there and then collecting the constants. So separately we have 3 integrals, 3/8, a half of that, and an eighth of that. So for this middle integral, the 1/2 cosine 2x, we would just do a basic u substitution, where u is 2x and du would be 2 dx. And then for this one, we'll do another basic u substitution, where u is 4x and du is 4 dx. And so separately, these integrals now are nothing we can't handle, so that'd be 3/8 x plus 1/4 sine 2x plus 1/32 sine 4x plus a constant. Okay, so what if we have a secant to a power times tangent to a power? So the idea is going to be very similar to some of the things we did with sine times cosine. So we would start with tangent cubed over the principal square root of secant. We would rewrite that as tangent cubed times secant to the 1/2. That way we don't have the fraction, to the negative 1/2. Tangent cubed, well, we are going to take one of those tangents and we're going to have tangent, so we're going to take, we've got tangent cubed times secant to the negative 1/2 x. So that would be the same thing as a tangent squared times tangent. So there's our tangent cubed. And then we have secant to the negative 1/2 x. And instead of having secant to the negative 1/2, we're going to have secant to the negative 3/2 times secant. Because if you multiply those together, that'd be, you would add their exponents. So negative 3/2 plus 1 would be negative 1/2. Now the reason we write it that way is we need a secant tangent for our du. So here in a second, you'll see why instead of leaving it secant to the negative 1/2, we wrote it as secant to the negative 3/2, secant to the first. Because we wanted this secant and this tangent for our du here pretty soon. So we would have, let's see, instead of tangent squared, we're going to do secant squared x minus 1. And then we've got our secant to the negative 3/2, and then we're going to have our secant tangent. And then, like the sine cosine, we're going to distribute and split up the integrals. So if we distribute, if we take this times secant squared, and then we're going to do this times negative 1, we're going to end up with secant to the 1/2 secant tangent dx minus secant to the negative 3/2 secant tangent and that way, if you let u equal secant, then du will be secant tangent, which we have now, secant tangent. We have that because we split up the secant to the negative 1/2. We split it into secant to the negative 3/2 and secant to the first. That way we'd have that secant tangent. And we created the single tangent by taking the 3 tangents we started with and writing it as 2 of them times another one. And then we can do a similar u substitution for the other integral. So now, using our u substitution, we end up with 2/3 secant to the 3/2 x plus 2 secant to the negative 1/2 x plus a constant. So notice that we forced tangent to have an even power, changed tangent to secant, and saved a secant tangent for du. So we created a secant tangent for our du, and then we had tangent go to tangent squared so we could swap it out for secant squared minus 1. So for this next one, we have a secant to the 4th 3x times tangent to the 3rd 3x. So let's give this one a whirl. So we have 4 secant 3x's to deal with. So why don't we go ahead and keep 2 of them together. And then swap that secant squared out for 1 plus tangent squared. The idea being that we now have, we're going to end up with this secant squared that's going to be our du. Because if we let u be tangent, the derivative of tangent is secant squared. So we're going to have this secant squared right here be our du. That's where this is headed. So we're going to distribute and split this up. So if we distribute and split up, we get tangent cubed secant squared plus tangent to the 5th secant squared. And if we let u be tangent, then du will be secant, well, it's going to be tangent. It's going to be tangent 3x. So it's going to be secant squared 3x times 3. And then same thing over here. Tangent 3x, so du is going to be 3 secant squared 3x. So using our u substitution, we'll end up with tangent to the 4th and a tangent to the 6th. So we clean it up a little bit. We'll have 1/12 tangent to the 4th plus 1/18 tangent to the 6th. So this time we made sure that we had a secant squared available if we let u be tangent. And for this last one, what if we just have a tangent? We can handle that very similar to the way we handled just when we had a cosine. So if we do 0 to pi over 4 of tangent to the 4th, we can write that as a tangent squared times a tangent squared. And then replace one of those with secant squared minus 1. And then distribute and separate. So we have a tangent squared secant squared. So there's our du. So if u is tangent, then du will be secant. So we'll have 1/3 tangent cubed from 0 to pi over 4. But then we still have this other antiderivative definite integral to work with. So we're going to swap tangent squared out again for secant squared minus 1. And the antiderivative of secant squared is tangent, and the antiderivative of 1 is x, so we end up with 1/3 tangent minus tangent plus x. We go 0 to pi over 4. So plug in the top, plug in the bottom, and subtract. You get negative 2/3 plus pi over 4, which is approximately 0.119. for that one. So now we have a few more methods that will allow us to find antiderivatives involving trig functions.